Picture this. You've rolled out a fleet of ESP-32-based smart street lights across a city, and a month later you discover a bug in the dimming logic. Without OTA, you'd need to send technicians with laptops and cables to every single lamppost. In practice, that's not just expensive, it's unmanageable. OTA, or over-the-air firmware updates, solves this by letting devices securely fetch and install updates on their own, just like your smartphone does in the background. In this lesson, I show you how OTA works on the ESP-32, why the partition layout matters, and how you can use ESP-IDF's OTA component to roll out updates remotely. By the end, you'll have the know-how to update devices in the field without ever touching them again. At its core, OTA is the ability for your ESP-32 to update its firmware over Wi-Fi without physical intervention. Think of it as remote surgery. Instead of opening up the device, you deliver the fix wirelessly. The process begins when the ESP-32 connects to Wi-Fi and contacts an update server. It then downloads the new firmware in chunks, writes those chunks into an unused flash partition, verifies the file with a checksum, and reboots into the new image. The original firmware stays intact until the very last moment, ensuring recovery if something goes wrong. Imagine it like dual booting your PC. One OS is live, the other gets patched in the background, and the bootloader decides which one to launch next. This design is what makes OTA reliable in production IoT deployments. OTA only works if you've structured your ESP-32 flash memory correctly. The flash layout needs multiple app partitions, so one can run while another gets updated. Typically, you'll see a bootloader partition, a factory app slot, at least 2 OTA slots, and an OTA data partition. A useful analogy is having 2 hard drives in your PC. You're booted from drive A while applying updates to drive B. After reboot, the system switches to the new drive if validation passes. This arrangement ensures that even if a power cut or crash happens mid-update, the device still has a known good firmware image to fall back on. If you neglect this partitioning, your OTA attempts will fail before they even begin. Let's step through the OTA flow practically. First, the ESP-32 connects to Wi-Fi and checks with an update server. This could be an HTTP, HTTPS, or even an MQTT-based endpoint. It then downloads the firmware binary in chunks, writing each chunk into the inactive OTA partition. Once the entire binary is stored, the system runs an integrity check, CRC or SHA-256 hash, to confirm nothing was corrupted in transit. The bootloader is then instructed to switch to this new partition. On reboot, the ESP-32 launches the new firmware, and if everything runs correctly, the update is marked as valid. If the device crashes or fails to boot, it reverts to the last known working image. This controlled sequence is why OTA is safe enough for critical deployments. Now let's make it tangible with ESP-IDF's ESP-HTTPS_OTA component. Imagine you've built new firmware and placed the binary on a local HTTP server. Your ESP-32 code simply needs to point to that URL, and the OTA function handles the rest: connecting, downloading, writing, and restarting. The elegance here is that you don't reinvent the wheel. The SDK takes care of the low-level details like flash writes and partition switching. What you, as the engineer, must get right are the fundamentals: defining the partitions correctly, hosting the firmware where the device can reach it, and ensuring proper error handling. Once those are in place, you can trigger updates by replacing the binary on your server, and every device in the field can pull it down automatically. Over there, or OTA, lets you update ESP-32 firmware remotely without using a USB cable. Here's how it works. First, the partition table must include 2 OTA slots, OTA_0 and OTA_1, along with factory and data partitions. This way, the ESP-32 can run one firmware while downloading the new one into the inactive slot. Next, in the code, we configure the OTA URL pointing to the server hosting firmware.bin. Using the ESP_HTTPS_OTA function, the ESP-32 downloads the file, writes it into the inactive partition, and verifies the update. If successful, it automatically restarts into the new firmware. Finally, to host the binary, compile with idf.py build, copy firmware.bin, and serve it from your PC using a simple HTTP server. After years of rolling out OTA, I've seen patterns in what goes wrong. The first culprit is partition mismatch. If your partition table doesn't have at least 2 OTA slots, the update fails silently. The second is connectivity. Often the firmware URL is mistyped or unreachable. With HTTPS, mismatched clocks break certificate validation, so always sync NTP time before secure OTA. Power loss is another risk. But thanks to dual partitions, the ESP-32 can roll back if an update fails midstream. Finally, logging too much during OTA slows things down. My rule of thumb: log essentials, but strip debug chatter in production. OTA is robust when designed carefully, but careless setup can leave devices stranded. To truly master OTA, you need to push beyond the basic HTTP example. A good next step is implementing secure OTA using HTTPS. This involves generating a certificate and having the ESP-32 validated before downloading. Another extension is OTA triggered by MQTT. Your device subscribes to an update topic, and when you publish a command, it fetches new firmware. Finally, add version checking. Have the ESP-32 download only if the server's version is newer, saving bandwidth and wear on flash. These mini projects will give you hands-on practice with real-world patterns, preparing you to scale OTAs safely across fleets of devices. In this lesson, you've seen why OTA is not just a nice-to-have but a necessity in IoT projects. You learned how ESP-32 partitions enable safe updates, how the OTA flow works step by step, and how to implement OTA in practice with ESP-IDF. You now know the common pitfalls that derail updates in the field, and you've got concrete project extensions to explore, from HTTPS security to MQTT-driven fleet updates. With these skills, you can design ESP-32 systems that remain flexible, secure, and maintainable long after deployment.